Okay, the title of chapter 6 is Exponential and Logarithmic Functions. Sounds daunting. It is. It's not that bad. We'll take a little piece at a time. There are 7 sections. We will get through at least half the chapter, but we'll come back and hopefully you'll be able to jump right back in and finish it up. We'll see. Your memories are better than you think after a few weeks out. It doesn't take much to gel them and get them going again. First, we're going to do exponential growth and decay because it's supposed to be something you're kind of familiar with from algebra. In algebra, the idea was to study linear things, learn how to graph lines and things, and also get your introduction to quadratics and the quadratic formula and factoring, stuff like that. And also, you're supposed to have a little bit of an introduction to exponential functions. Oh, nice shot. You play basketball, dude? All right. Okay, so your eyes need to be on page 296. That's where we're starting. And quite a bit of stuff to tell you. None of it's very hard, but there's quite a bit of it. So try to stay with me. First thing is we're going to look at the standard form of an exponential equation. And it is y equals ab to the x. And it is this that makes it an exponent, where the variable that could be anything is sitting in the exponent spot. This right here is the beginning amount. Beginning amount of what? Beginning amount of whatever you're talking about in the problem. That's the beginning amount. This is the most important part. It's one we're going to spend the most time discussing today. That is called either the growth or decay factor. Now, in math, whenever we use the word factor, we mean something that is multiplied by something else. And surely that is a factor because it will be multiplied by itself this many times. So it is a factor. If this was a 4, B would be a factor 4 times. You follow me? If this were 4. It's not. It varies. It just keeps getting bigger and bigger and bigger, or smaller, depending on which way you go. This thingy right here, that is usually time. Usually. So I'm going to put that in parentheses because it's usually time. Sometimes, as you will see as we go through the chapter, not today, but sometimes it's something like altitude. As you go up in the atmosphere, pressure goes down. And it's an exponential relationship. So it's not always time, but most of the time it's time. Okay? And this right here, this is what we get. And it's constantly moving. As x goes up, this changes, or as x goes down. This value keeps changing. What this is the amount of what? Whatever you're talking about. Money, people, all kinds of things it could be. It's the amount after X time has elapsed or has gone by. So if I let X be 4 hours or something like that, then I use B 4 times, I multiply by the beginning amount, and that's how much I have now. And if I make it 5 hours, then this will change to whatever that 5 hours will make it change to. So you need to be able to look at this standard form. It's got 4 pieces, and you got to know what each one's going to have. What's happening? Each one. Okay. We could call this, instead of y, we could call this f of x because the amount after time is a function of how much time has elapsed. Now, this is the only part we haven't really discussed much right here. Here's the deal on this. Summarizing this right in here, this is the most important part, like I said. If B is greater than 1, that means, and this is how we do it, this is how I write it in geometry, might as well get used to my notation. This thing right here, it's an equal sign with an arrow on it. That's a verb. says if B is greater than 1, it means or implies or we believe, not we believe, it is true. If B is greater than 1, then, if you will, then you have a growth model. And if B is between 0 and 1, you have a decay. What if it is 1? You got nothing. Because you just keep using 1 over and over and over, and that's dumb. That's not exponential. That's linear. So, and we will never have B be negative, not in this class. You can study that later if you want, but no. B is always going to be a positive number, always positive. But if it's between 0 and 1, in other words, this is interpreted, if you're fluent in math, this is interpreted if B is a fraction or a decimal less than 1, you know. If B is a fraction, you got a decay. If B is something greater than 1, and it doesn't have to be a whole number, it just has to be greater than 1, like 1.4. So if this is an improper fraction, if you will, something that's greater than 1, it's going to be growth. And think about why that would be. This value will get bigger and bigger and bigger. In other words, grow if I keep using something bigger than 1 over and over and over, like 2. If I use 2 times 2 times 2 times 2, every time I use another 2, it doubles the n, right? And so if this thing is a than 1, even 1.02, you multiply something by 1.02, it gets a little bigger. Multiply it by 1.02 again, it gets a little bigger. So it's growing, but it's not very fast. However, if this is like 1/2, then you keep using 1/2 over and over and over again this many times. Every time you take something times 1/2, it cuts what it was before in half. You multiply by 1/2 again, and now your half is what you're half of what you were before that. So if it's a proper fraction, you keep using it over and over and over again. You keep multiplying by something smaller than 1. You got to keep making something smaller and smaller and smaller. Okay? That make it sense that this would be the case? I hope. This is what a growth model looks like. In a general way, a general shape for a growth model starts asymptotically over here, crosses the y-axis, and goes up pretty darn fast. This is a growth graph. If you have a decay graph, it means you start pretty high up, but it keeps getting smaller and smaller and smaller as time gets bigger or as x gets bigger. And it looks like that. Both are asymptotic on the x-axis. And when I say asymptotic, I mean this branch here and this one over here. They just keep getting closer to the x-axis, but they never arrive. Which means that the range of all exponential functions, the range, is greater than 0. The domain's all real numbers. Every x on this axis that you want, I don't care how far out you go on this one or how far out you go here, you will hit the graph if you go up high enough. It's not very far. It's not very hard to go up high enough if you're out here. You got to go right there. Not very high. But if you're back here, you got to go up quite a ways before you get it. But you will hit it. It keeps coming out like this forever. Same with this one. The farther out you go here, the farther out you got to go to hit it. But every single x works. But the only y's that can be produced are positive. So the range is always positive, regardless of what you got. That's a growth. This is a decay. How you doing so far? Just a bunch of explanation, just talking at you. Now we're going to erase this. Some of you, is that a picture you took? Did you get me in it? Did you?
I could if you want.
No, I don't want that. No. Take a picture of the board. That's fine. That's okay. All right, so I'm going to erase that. If you have to review it again and you really want to get to it, we're recording. Just go to YouTube. Hit 6.1. Okay. So now let's see. I'm going to erase this and let's see if you can, hopefully, if you've taken some notes or you can remember what was up here. We're going to apply it to example 1. It's not very hard. Well, actually, let's just apply it right now because it's so not very hard. So why am I going to put it on the board? Look at page 297 at the top. Example 1, it says, tell whether or make the decision whether each function represents an exponential growth or an exponential decay. What do you think about the first one?
Growth.
Why? What is? Don't say it. 2, which sits in the B position, right? In this one, just for the fun, just sake of see if you understand that. In this one, example 1A, what is A? From what you see up here on the board, what is A in this function?
1.
1. So it didn't bother to write it. You understand that?
Yeah.
And B would be 2, and then X and Y are where they belong. And so the thing that's being powered, the thing that's got the power on it, that's B. There was nothing written here, so we assume that A was a 1, if anybody was wondering. And so since B, which is 2, is greater than 1, we have a growth going on. Obviously, B is going to be a B will be a decay. What is A in the B? 1. And the B is 1/2, and because it's between 0 and 1, we have a decay. And if they show you graphs of both, then you can see that it takes on the shape that I told you it would. Look at the bottom of page 297, near the bottom, on monitoring progress. Is number 1 in monitoring progress a growth or decay? How about the number 2?
Decay.
How about 3?
Decay.
How about 4?
Growth.
At least the ones that answer. Seem to answer correctly. Does the rest of you follow along? Everybody got it? All right, moving along. Now, I'm not going to turn the page yet. It's the bottom of page 297 because, as always, we muddy the waters with an alternate form. Still an exponential form, but it's an alternate form, which I'm going to put right down here. I'm going to put it in blue so you can still see it, but so that you know that it's different because I haven't got much space up here. It's all got to be on the recording. Okay, listen. This is what you look for when you're doing this blue form. You look for this in the words. Percent per time. And when I say time, I mean like percent per year or percent per hour or something like that. So time is something that's going to be replaced, and it'll go on like this. If you see this, this is the form of the exponential model you want to use. Y equals A times 1 plus R to the X. So I've replaced B with something else. This is a growth. I'll put it right up here in red. This is a growth. This form of it, Y equals A times 1 minus R to the X, that's a decay. Now, here's the important part of me writing this up here, this piece right here. All right, you've got to get distinguished in your mind. And it's subtle, it's little. It's a little thing, but boy, is it important. This right here, in each case, just like I showed you before up here, this piece that's being powered, it's got 2 pieces. It's a binomial that's being powered here. That whole chunk is called the factor. And in this case, it's a growth factor. It's that whole thing that's going to be used over and over and over. We call that the growth factor. And this is the growth factor. But this, get another color. All nice and pretty. Big colorful. This part in both cases, not with the sign, just this part right here. That and this, that's called the growth rate. This is the rate, the growth rate, or decay rate. And you got to get it straight which one they're talking about in the problems. When they use those words, they'll either say the growth factor or they'll say the growth rate. And you got to know the difference. And you got to watch for it. It's not just something we can just arbitrarily and use them interchangeably. They are not the same thing. This right here is the percent. If something is growing at 2% per year, then this number right here will be 0.02. If, like a car or a piece of machinery, we've even talked about this before with some problems that we've done. If something is losing value, that's usually when we use this. Something is losing value, or a population of a town or city like Detroit, that happened a while ago. People are moving out faster than they're moving in. They're losing population. That would be your decay rate. If they're losing people at a rate of 3.2% per year, then this is 0.032. Okay? This is losing. This is gaining at a certain percentage, and the percentage has to be changed to a decimal to use it. Okay? And it's really important you understand the difference between the factor, which includes the 1, whether it's 1 minus or 1 plus, and the rate, which is what you're adding or subtracting. And the rate is usually expressed as a percentage and must be changed to a decimal before you can. Okay, that's what's at the bottom of page 297. Now we're going to try it. It's the same thing I just told you about. And now I am going to have to erase the board. Okay, we'll talk about the value of a car losing. It's going to lose value instead of gain. until it's worth nothing because it's in the salvage yard. What's interesting about this is that with cars, especially vintage cars, you can have a decay that over time may begin to grow if you take good care of it and, you know, fix it up. It can be worth a lot more later. So it doesn't stay exponential the whole time if it's a vintage car. If it's not something you want to work on and you just let it fall apart until it dies and now it's in the salvage yard, then it does follow an exponential and it just stays worthless until it's printed on. Okay, so here we go. In example 2, it says the value of a car, Y, in thousands of dollars. Pay attention to that in the parentheses because all the numbers are going to be in thousands. The value of a car, Y, in thousands of dollars can be approximated by the model. Y equals 25 times 0.85 to the T. Okay, notice that they've replaced X with T because it's time. Well, it's not time to replace it. It's because that's what it is in this thing. This, if you really want to know, really should be replaced with V for value. So I think I will, even though they put Y. I'm going to call it V for value of the car. So this is the value of the car as time goes along, and we can tell that the value of the car is decaying. You expect that from cars. They don't gain a value. The longer you drive them, the less they're worth. Okay, so it says in the A part, tell whether the model is a growth or decay. We already discussed that. It's a decay. Okay. Identify the annual percent increase or decrease in the value of the car. So here's where that other part that I just erased comes in. This thing right here represents this. And they want to know this, which is what? 0.15, which is 15%. Does everybody know where the 0.15 came from? This right here, even though they don't write it as 1 minus R, they wrote it as the result of 1 minus R, and they want to know what R is. So 1 minus R is 0.85 is what they're saying. And so R, if I kick that over here, R is 0.15 because 1 minus 85, $1 minus 85 cents, 15 cents, yeah? So 15% decrease. That's how this thing's decaying. We say it's depreciating at 15% per year. That's what this represents. And it won't be written 1 minus R. You have to interpret it. This is the result of 1 minus R, and so R must have been 0.15. Okay, so that's the B part. That's the kind of thing you got to come up with. It says it's a decrease of 15% a year. It says estimate when the value of the car will be 8,000. What's the value of the car when it was purchased? What? Can you tell from this? How much was it bought? How much was it purchased for? So when we started the clock on this depreciation, it was purchased at $25,000, not $25, because it says in thousands, right? Okay. So the way we figure out on here on the calculator, the way we figure out when it will be 5,000, we're looking for an X value. When the value of the car, which is the Y value, is going to be 8,000. So first of all, we got to get it graphed. So everybody graph this function in their calculator using X for T. So in the Y equals screen, you're going to have 25 parentheses, 0.85, close it, raised to the X. Now what about a window? Let's think about this for just a minute. What's about, just give me a guess if you have any idea, what's about the lifetime of a car?
30
Yeah, people around here will say 30. Most people say 10. We're going to go out. We'll go out to 20. We'll get in there somewhere, okay? So go for your window, go from 0 to 20 on the X, counted by, I don't know, 5s. And on the Y's, we're talking about the value here. What's the initial value, according to our graph? What's the initial value? 25. So we want the maximum to be about 30, just so that we build a little buffer zone in the top. We also want to be able, I'm going to the Y min now. We also want to be able to, because we want to see that curve come down. So I think I'm going to let the Y minimum, if the max is 30, I'm going to let the Y minimum be like -5, so that I've got a little buffer on the bottom of my screen. You with me there? Okay, and I'm going to scale that by 5s also. Now graph and see what you got. you've got a decaying value, right? If we have all that window the way we designed it. So I'm going to give you that. I'm going to look at that. Here's the window we put together. And here's the equation we were graphing. That's right up there on the board. Okay. So how do we figure out from this when the value will be 8,000?
Yeah, to figure out when the value is, I put in y is 5.
So you went to a y because the y value is 8,000. This is, they're saying this is 8,000. What is this at that point? And the only place to put in y values is in the y equals screen.
Yeah.
So we go to y equals, we go to y2 and put in the number 8, not 8,000, 8, right? 8, not 8,000, because everything's in thousands in this problem. So we hit graph, and I get a red line that looks like this. I know it's hard to see. Can you all see that without the glare?
Yeah.
It looks like that, kind of. Okay, for those of you viewing, it looks like that. And what I want to do is find that intercept point. So I go second, calc, and intersect, and I hit enter, 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 and it goes to barely more than 7 years. That's the x value. That's the t value when y is 8. So this thing will depreciate. You purchase it for $25,000. In 7 years, it will only be worth 8. But you got 7 years worth of driving out of it. Transportation, you pay for it. Okay? Everybody understand the 3 components of the question here? Growth or decay. What's the beginning? Well, what's the percent increase or decrease? That's hidden in this right here. That is 1 minus r, so r is 15% to answer the B part. And the C part is graphical. We found it to be about 7 years. Everybody good or not? Are you just nodding at me because you tired of me yakking at you? Do you understand what's going on here? I hope you can do a problem like this. Okay. All right, example 3. Now they're not going to give us the model. They want us to write it. Not going to be that bad. It says, in the year 2000, the world population was about 6.09 billion in the year 2000. During the next 13 years, the world population increased by about 1.18% each year. Oh, look, I told you what to look for. Watch for in the problem. It increased. That means we're going to be using 1 plus r by about that percent per year. That means we're going to be using that alternate form, the alternate form of the equation. And since it says increase, it's going to be this one. Y equals A times 1 plus some rate to the t. That's what we're going to be using, and we got to fill in the gaps. The one thing you don't fill in, folks, you don't fill in the y and you don't fill in the t because those are both changing. But this and this are given values in that problem if you can find them. What is A? 6.09 is A. If we talk in billions, you got to write this is in billions, okay? We don't want to put all those zeros on there. Times, and then what will this be in here?
1.1.
It just be 1.2.1.
What percent is it growing at?
0.118.
What is the percentage?
1.18%.
Percent
Out of 100.
out of 100, yes. Remember the rate, the r that's going to be here, 1 plus, what I'm going to add there, it's got to not be a percentage, it's got to be a decimal. You follow what I'm saying?
Yeah.
No?
It's all over 100.
It's only growing at barely more than 1%, the world population, which is really quite significant, but it's only growing at 1.1. That's like a penny and a little teeny tiny bit more of a penny. That's not much. We have to express all percentages in our calculations as decimals, and a percentage change to a decimal is going to swing over 2. This is equivalent to is 0.0118. This is like, I mean, if you think about this in dollars, if you wanted to, because the percentage, this is like the 1 penny and a bit more. See that? This is going to be changed to a decimal. So it's 0.0118 to the t, and even better, 1 plus something small is just 1 point that. So that thing that I wrote for you is where it says it's either 1 plus r or 1 minus r is never written with 1 plus or 1 minus. It's never done that way. You get a result. But when it's a growth, it's a lot easier to identify the rate because there's your 1 plus. I mean, it's 1 and then a little bit more. This is your growth rate. It's a lot easier to see than it was with that 0.85, which was a decay rate of 15%, right? This is a lot easier to see, but it's still written without the plus sign. This never shows up in the final offering of it. Just gives you a way to find R, shows you how it's related. You see what I'm saying?
Yeah.
Growth rate would be, so you take that and you go, oh, growth rate's 1.18%. It's a lot easier to tell here than it was in the last one, because the last one required a subtraction that you do. It's not in the right. Okay, so it says, write an exponential growth model given the population y in millions, t in years, 2000, estimate the world population in 2005. How would we do that?
So we'd have to change,
You could graph it, but you don't need to. Just put a 5 in here. Now listen, the reason why we don't put 2005 in there is because they've been telling us throughout the beginning, the whole problem, that this thing started. We started the stopwatch on this thing in the year 2000. So if you want to predict how many people are going to be in the world in 2005, then this is not 2005. That would be if you let T be the time the day Christ was born. Do that. This is not 2005. This is 5. It'll account for when things got started. So now we'll just go to our home screen on our calculator and put a graph. You could graph it, but there's no need. Just plunk this in and raise it to the 5th. 6.09 parentheses. 1.0118 closing phase to the 5th. It looks like 6.46 billion about. Okay. B part says, estimate the year when the world population was 7. So now we got a graph because now we got a y value. We want to find the next one. And I have not taught you people, if I were to put into this equation that we have, if I were to put 7 here, which is the population, this is the value of the population. If I were to put 7 here, you do not have the means yet to isolate T algebraically. You will before this chapter's over. But you don't right now, which means your only option for answering this question is with the graphic, okay? So we're going to go to y equals, go there, and put this very equation in that we came up with. And let's try to decide, before we actually hit graph, let's try to decide a decent window for this. We're letting T be the years, and it starts in the year 2000, so I don't think we'll go much beyond to 2020, mainly because this book wasn't even, it was published before that. So I'm going to go 0 to 20 again on my axis. And the y's start at 6.09. However, as I said before, it would be nice if we could see the x-axis. So I'm going to let the y minimum be -2. And the y maximum be 10, because the world has not reached 10 billion yet. So I'm going to let it be 10. That's the population. I'll count that one by 1. Now graph it. Looks like a line, doesn't it? This is what I get in the window that we designed. It looks just like a line. It's not a line. It's a piece of a really, really slowly bending curve. It's starting to exponentially grow. But look at the growth rate. It's practically 1. Little tiny bit more, which means it's not growing very fast. Fast enough to be alarming if you live in this world, but it's not growing very fast. So you're looking at a piece of a very, very slowly growing curve. So the question asks, estimate when the world population was about 7 billion. So we go to y equals and type in 7. That's our line again. And we see it intersects the curve in the thing that we decided on. So now we're going to go find its intersection. And it looks like 11 years after, or almost 12 years after the year 2000. So somewhere in the year 2011, we crossed the 7 billion threshold. It's this predicts it. Did anybody have trouble doing that? Everybody needs some help with their calculator? So basically, folks, the moral of this story is if they want you to predict how much you'll have after some time, just plug it in. Just replace this with the T in the home screen. Just plug in the number and crank it out. But if they give you a value and they say, when will it reach this? And you got to find this, your only option is to graph and find intersects. Graph this side, which was the 7. Graph this side, which is the predictor, and find where they intersect to find the T value that goes with it. Okay, it's a solution method. Graph one side in Y1, graph the other side in Y2, find out where they cross. In this case, it was 11, almost 12 years, so about 2012 is when we crossed that 7 billion mark. All right, so these last 2 examples, there's only 2 left, 4 and 5. If you've been kind of dozing because it seems pretty easy to you, you better wake up now because this problem, example 4, is the one that people stumble on. So please try to get as much as you can from it and don't stumble. Some of you'll go, ooh. What does it say? Here's what it says. The amount Y in grams of a radioactive isotope chromium-51. None of that is important, just that it's radioactive and it's decaying. That's the most important part, it's decaying. It says the amount in grams of this isotope remaining after T days is Y equals A to the 0.5, I'm sorry, A times 0.5 to the T over 28. So that's it, right?
Yeah.
Okay. Where A is the initial amount in grams, we already discussed that. What percent of the chromium decays each day? That's a loaded question because what we've got to do is take this equation, Y equals, what was A? It's just A is just A, right?
Yeah.
And it was 0.5 here to the T over 28. And what they want us to do is they want us to figure out this piece of it right here. We've got to figure that out as a 1 minus something so we can figure out what is decaying every day. What percent of it is decaying every day. That's a hard thing. Pay attention to how we do it. First thing we do is we take, oops, leave the 0.5 there. We take the 0.5 and we raise it to the 1 over 20 to the T. In other words, we pulled the T off of there. There's an understood 1 right there. There's your 1 over 28 right there. And I pulled the T out here so that it behaves like the exponent usually does. Instead of being combined and tied up with that 28 and the division and all that kind of stuff, I pulled that T off of there so that it sits in the spot that I'm used to seeing it in by itself. That's a legal thing to do. It's just not something that's done very often. It's not a very common move. But you understand that move? Everybody okay? Then I evaluate this because now this is just a number. I just don't know what it is. I'm leaving him hanging out here. Up here with that T involved, I couldn't raise 0.5 to anything up here because that was a variable. So I removed the variable out to here. And now the stuff in here that's being raised to the T, just a number. It's just a number. And I need to find out what it is. So go to your home screen and take 0.5 raised to the parenthesis 1 divided by 28, close it. And then write down in here what you get, which is 0.9755. I'm going to go to another 5. That's an approximation. But you need these guys in here that are the factors, the growth or decay factors, are extremely sensitive to change. So you want this to be fairly accurate. I mean, several decimal places. These are really sensitive. You make a small change in this, you make a big change in the outcome. So you got to have these about as accurate, pretty accurate. And that now is raised to the T. And now you can tell. Yeah. So we go, this is what you do in your calculator. You just go 1 minus, and then you go second function and the negative sign at the bottom. And it'll subtract the answer without any approximating, at least according to the calculator. You understand that? 1 minus answer, and that is 0.0244. So R is, well, as a decimal is 0.02445, which is what as a percentage? What's this as a percentage? 2.445%. That's losing every day. That's the percent decrease every day. Now, why in the world would they start it out this way to begin with? Have you seen in biology and some other science classes and things you've had? Radioactive substances are all studied according to their half-lives. The substance gets cut in half every 28 days. The amount of it left after 28 days is half of what it was 28 days before. That's why they express things this way. This is how scientists study it. You want to know percent per day, you got to know the math to get to here and change it to this form so you find rate of decrease. And the hardest part of this is getting from here to here and remembering what to do. Get that T out of the way so that you can find a decimal that belongs to that part. It doesn't seem very hard, but when you guys encounter it, you're going to go, what did she do? Go back and down the form and look. It's right there for you in great detail. Go look at the example and try to follow it. Is that enough about that one?
Yeah.
Last thing has to do with growing money and investment. You've all heard those words before by now, haven't you? When you put money in the bank or when you put money in an investment and it grows, it means you get back more than you put in because you let somebody use your money for a while. It's a fee for letting them use your dollars. Okay. So if instead of buying that car for $25,000 when you graduate, Dad gives it to you, or gives you the money to buy it, or you get a whole bunch of money from all your relatives, you pile it all together, you get $10,000, go buy a car, you've lost your money in 7 or 8 years. Whereas if you took that $10,000 and invested it, by the time you're my age, you got a big chunky change if you're careful. Then watch where you put it. This is a growth model for percent per time. We will talk about a continuous growth model as we go through the chapter. But this is A equals. And after people see this and they start to use it, they say, can we have a cheat sheet on the test? No, never, not ever. Get this stuff in your head. Now, that is the growth rate for money as a percent per time. Look at the 1 plus. See it? 1 plus. This one it looks familiar. This is 1 plus because it's growing, but you're going, but that's supposed to be 1 plus R. Here's what happens, folks. Your bank, if you put some money in the bank, will take your money and they may pay you 4 times a year instead of annually. You'll always get an annual interest rate. They'll always say it's gonna, you probably heard this on ads on, you guys probably won't listen to the radio, but have you ever heard of an APR? It's annual percentage rate. That's what it stands for, APR. So they'll say that we'll pay your money compounded quarterly with an APR of 6%. Well, folks, they're not going to pay you 6% every quarter. Every quarter means every 3 months. They're not going to pay you 6%. They're going to pay you a fourth of that 6% because it's an APR. That's what this is doing. N is the number of times they will pay you per year. They pay you monthly, then N is 12. They pay you weekly, then N is 52. They pay you quarterly, then N is 4.
So N represents
The number of times per year that they will compound your money for you. So the interest rate is that this R is an APR. So if this is 6, they're going to divide it by 4 and only pay you 1.5% per quarter. So that's a total of 6% for the year. Are you following me or not? That's why this is not just R. Also, this exponent up here, this would be time in years. But they will pay you, like if you're going to invest it for 10 years, then this is 10, but they're going to pay you 4 times a year. So they're going to pay you 40 times. That's what this is. And so the N is used twice. They're going to split the interest rate up into N pieces, but they're going to pay you N times that number of years at this rate. So N is the number, and it's used twice. N is the number of times per year they will pay you. T is always in years. R is always a percentage. It's an APR every time. This has to be a decimal when you write it. This is the amount of money you took to the bank the first day. This is called your principal or the principal investment. This is the amount that's actually in your account as time goes along, and that grows. Because you're leaving your money there to let people use. It grows. The value of it grows. They don't just set it in a vault and it just spontaneously grows. They use it. They invest in different places. People pay them back a certain amount. They'll pay you. So just for an example, so you understand how banking works and the reason why bankers are always rich and they never take a risk, hardly ever. Sometimes they do. The reason why is because if you take your money in and say, I want to put this in a certificate of deposit for 10 years, here's my investment, and you just walk away and leave it and you watch how it grows. You see, get the paper, how it grows. They're going to take your money and they're going to pay you. Let's say they paid you at 5% per year. That doesn't happen today. But I go in and I say, I got to have a loan to buy a house. And they say, okay, it's going to cost you 9% annually. So you're going to have to, we'll give you the $100,000 you want to buy your house, but you're going to have to pay back that $100,000 plus 9% every year. The difference between the 9% I borrowed it at and the 5% you're making, that extra 4%, that's what the banker makes. And that's why they're always rich. They don't very often. If you're a good banker, you don't go under. The only time you go under is if I, as the borrower of the money, fail to pay back my loan. If I go into default, then what they do is they come and they say, okay, get out, you're evicted. I'm going to take your house and sell it to pay your debt. So they still don't lose. Unless there's no one to buy my house. Then they're in trouble. That's where the risk is. And the housing market fell apart in 2008. I mean, it fell to the ground. And that's the reason why so many banks had to be supported by you guys were around, but you weren't paying attention. That's why the banks had to be supported by the government, because they were all folding. People could not pay back their loans, so they couldn't pay you for your investment. And you're pissed because you got a contract. You want your money out of that. People are all scrambling to go to the bank. Give me my money. I want my money now. You guys are doing. And they go, we don't have it. It's in Miss Johnson's house and she can't pay. I don't know what to tell you, man. It was a bad deal. Housing crunch was bad. Anyway, so that is a risk that some bankers take, but they always make that margin. I just need to talk about this someday. Let's go on. Example 5 says, you deposit $9,000. Stop right there. What is that in this thing? That's P. You deposit $9,000 in an account that pays 1.46. What is that? R, but written how? 0.0146. Not much. Find the balance after 3 years. What is that? T. When the interest is compounded quarterly. What's that quarterly interpreted as?
4.
That's N and it is 4. So we put all the stuff in here. Say A equals, what did we invest? 9,000. 1 plus, what was the rate as a decimal?
0.0146.
Divided by 4. Raised to the 4 times 3. So you could put a 12 here if you can do the arithmetic, and I know you can, but that shows all the pieces. Y'all see how we got that out of the words? Not very hard. Now, you can put this on your calculator immediately, just like it is, and get the answer if you're careful. This is the syntax for your calculator. You would type in 9,000, parenthesis, 1 plus, parenthesis, 0.0146, divided by 4, close it, raised to the, and you can even put that in parentheses if you want. I'm not, because you better be able to do that arithmetic. It's 12. That's the syntax you would use, and your calculator knows order of operations and spit out a number. We want it to the nearest penny. This is on your home screen, folks. This is not a graph. $94.02? 21? Everybody able to do that? 94.0221, which means over the 3 years you left it invested, you made $402.21 by just letting it sit there. But you had to leave it there for 3 years. And you made $402 in 3 years by just leaving it alone. Okay? All right. So I guess I better write the answer up here. 94.0221. That's the value. That's the amount that's in your account now. This is your principal, the 9,000, and then here's your 402.21. Okay. Guys think you can handle it? Okay. Here's your assignment. Those of you doing it on paper, it is. Are you ready to write?
7 seconds.
Oh, and by the way, and it's in Big Ideas, or it's in Power School right now. If you did not score a 75 or better on the test, you're doing this on paper, this entire chapter. Unless you make up this test and score better than 75. At that point, you can go back to Big Ideas. If you scored less than 75, that's 74 or less, you've got to be doing this on paper. So here's the assignment. 1, 2, 3 to 43, odd, and 46. 1, 2, 3 to 43 odd, and 46. And I will pass back your test in case you're wondering what you got. You gotta decide you gotta do this on paper. Take a look at that. There you go.